Imagine this. You fall feet first toward a black hole. Your feet hit the gravity first, they being stretched into a noodle while the watch on your wrist slows down to almost a stop. Meanwhile, from far away, you appear to freeze in time. Is that how movies show it? Not quite. In the next 10 minutes, we're going inside a black hole, the science, the wild theories, and the biggest sci-fi myths busted. Black holes are regions of spacetime where gravity is so strong that not even light can escape. They're defined by a boundary we call the event horizon. Cross it, and classically, there's no coming back. Black holes come in different sizes. There are stellar black holes, which are a few to tens of times the mass of our Sun, and then there are the supermassive giants at the centers of galaxies weighing millions to billions of suns. And they aren't actual holes in space like pits. They are extreme warps in the very fabric of spacetime itself. So, if they swallow light, how do we even see them? We can't see the black hole itself, but we can detect them by the chaos they cause around them. It's like hearing the universe's drumbeat. Okay, let's get back to you falling in. That difference in force stretches you out into a long, thin shaper process physicists cheerfully call spaghettification. You'd literally be pulled apart like a noodle. But here's an important twist. The experience depends on the size of the black hole. For smaller, stellar mass black holes, the tidal forces are absolutely lethal well before you even reach the event horizon. But for a supermassive black hole, the tidal difference at the horizon can be small enough that you might cross it without feeling anything dramatic at all. You'd pass the point of no return without realizing it, and only later, much closer to the center, would you get torn apart. Now, let's look at this from the outside. General effect dilation. As you get closer to the event horizon, a distant observer would see your clock appear to slow down. The closer you get, the slower time seems to run for you until you appear to freeze completely and fade away, your light stretching out and becoming redder. So, paradoxically, to you, falling in happens over a finite amount of time. But from the outside, it looks like you never quite make it past the edge. classical general relativity predicts that at the very center, you reach a singularity, a point of infinite density, where all the mass is crushed into an impossibly small space. But infinities are a huge red flag in physics. They usually mean our theory is incomplete. Most physicists expect that a theory of quantum gravity something we do and have yet will replace the idea of a singularity with something else. Inside the horizon is one of the greatest unknowns in science. And this is where things get even weirder. It's called the black hole information paradox. If this radiation is purely thermal, it carries no information. So, if a black hole completely evaporates, what happens to the information about everything it swallowed? That's the paradoxa, major puzzle at the heart of modern physics. Resolving it has led to some wild ideas. Maybe the information is encoded in subtle ways in the Hawking radiation. Or maybe it's stored on the event horizon itself, like a hologram. One controversial proposal is the Firewall hypothesis. This idea suggests that instead of a smooth, uneventful horizon, an infalling observer would hit a high-energy wall of fire. This would solve some quantum problems, but it breaks the long-held belief that crossing the horizon of a large black hole should feel like nothing. The Firewall debate shows just how much we're still arguing at the most fundamental level. Okay, let's talk about the movies. How do they stack up against reality? Interstellar is often praised for its realism. It had a consulting physicist and did a great job modeling gravitational time dilation around a massive object. But it also had to compress enormous timescales and simplify the brutal tidal effects to tell its story. In many other sci-fi movies, black holes are treated as portals, wormholes, or convenient warp gates. That's entertaining, but it's purely speculative. In the real universe, the event horizon isn't a magical doorway. It's a one-way trip to oblivion. But they usually skip the messy physics, the singularities, the quantum paradoxes, and the sheer violence of it all. So, what's next for black hole science? Our telescopes are constantly improving. The Event Horizon Telescope is getting sharper, allowing us to see magnetic fields and flares near the horizon. Gravitational wave detectors are finding more and more black hole mergers, letting us probe gravity in its most extreme form. The ultimate dream would be to detect Hawking radiation directly, but that is an incredibly difficult challenge. Black holes are the universe's greatest thought experiments. They push our theories to the absolute limit and force us to come up with new ideas. They are part terrifying, part profoundly beautiful, and they represent the ultimate battleground where Einstein's relativity meets the strange world of quantum mechanics. If you enjoyed this deep dive, hit that like button, subscribe, and let me know in the comments, what sci-fi black hole scene should we analyze next? I'll pick the best one and break it down in a future video. Thanks for watching.